This is chapter 11 review. We want to look at page 658 and we're going to practice some problems to make sure that we are on top of this section. So here it says which of the sequences whose nth term appears in these problems converge and which diverge. This is a good for the series, good practice, because when I look at those, I'm going to be taking the limit as n approaches infinity of every single one of them. And what I notice happen on this one. What do you notice? What is this limit equal? As n approaches infinity. So keep in mind, if I take 1, negative 1, 1, negative. So if I put n equal 1, I'm looking at 1 minus n equal 1, 1 plus 1 over radical n. That's 2 over radical n. And if I let n equal 2, I'll get 1 minus 1 over radical n. N equal 3. N equal 4. Of course, this is 0 and this is 0, but the limit as n approaches infinity of this will be 0 as well. So this limit will equal 0. Therefore, this sequence converge. So this is testing whether this limit exists or it doesn't exist. Keep in mind, for any of these numbers that we do, the limit doesn't equal 0. If this was a series, the series would diverge. Okay, to save time, I'm going to start pausing the video, copying down the problems, since they're all the same. On first batch of problems, on numbers 1 through 20, I think, it says, oh, wrong page. Okay, here we go. On 1 through 18. So all of these are the same. Let me just save time so we could do as many as possible. If I take the limit as n approaches infinity of 1 plus 0.9 to the n, if you recall, this is an exponential function and the base is between 0 and 1. This approaches 0. That would equal 1. Therefore, converge. Remember, if it's a sequence, if the limit exists, it converges. If this was a series, that will diverge by test for divergence. I'm going to mention that in every problem. This problem. Do you recognize if n equal 1? If n equal 1, I'll get the sine of n. Pi. N equal 2, sine of 2 pi. N equal 3, sine of 3 pi. So this is 0, 0, 0. So if I take the limit as n approaches infinity of the sine of n pi, that would be 0. Therefore, converge. Alright? I think they meant to make a cosine, but it's all good. How about here? Limit as n approaches infinity of natural log of 2n plus 1 divided by n. Well, that's infinity over infinity. By L'Hopital's, this is the limit as n approaches infinity. This is 1 over 2n plus 1 times 2. And the derivative of n is 1. So this is the limit as n approaches infinity of 2 over 2n plus 1. Wouldn't that be a 0 because 2 over infinity is 0? Therefore, converge. So here, you don't say converge by what, diverge by what, because if the limit exists, the sequence converge. Next problem up, I want to look at number 12. On 12, I'm taking the limit as n approaches infinity, and we did this too many times by now. I really want to take that to the n, so if I raise that to the negative 1 power, that will do. If I raise those, when you multiply those powers, you get negative n. So this is the limit as n approaches infinity of 1 plus 1 over n to the n, all raised to the negative 1. And we all know what that is. We did that too many times. That's e to the 1 raised to the negative 1. So that is actually 1 over e. Therefore, converge. Again, if this was a series, we would have said this series diverge by test for divergence. But those are sequences. So the limit is going to help out. If I start problem number 14 and take the limit as n approaches infinity of 3 to the n, and let me see, what am I really looking at? I'm looking at 3 over infinity, 0 to the 1 over infinity 0. What does that mean? Either I take log of both sides, or I rewrite this problem as e to the natural log of whatever you see. And that would be e. One of the properties of logs, I could move that up front. I forgot the limit. Let me fix that. I apologize. That would be the limit as n approaches infinity. And if I write this as e to the natural log of 3 over n over n. Now, that's going to be e raised to the limit as n approaches infinity, natural log of 3 over n over n. That's as n approaches infinity, 3 over, this will approach 0, that's negative infinity over infinity. So L'Hopital still apply. Remember we said plus or minus infinity, it doesn't matter. E to the limit as n approaches infinity. And what is the derivative of this? Now, I could simplify this and say that's natural log of 3 minus natural log of n. And if you don't see that, not a problem. Derivative of a natural log is 1 over the argument times the derivative of the argument. Wouldn't that be negative 3 over n squared over 1? That would be e to the limit as n approaches infinity. And let's see what this is. If I multiply by the reciprocal, this will be n over 3 times negative 3 over n squared. Those cancel out, and this cancels one of those. So I'm looking at a power of the denominator is a 1, of course. I'm looking at a power of, negative 1 over n. Wouldn't that approach 0? And e to the 0 is 1. Therefore, converge. Again, if this was a series, that would have diverged. Just saying. 16 is next. I can look at this as 2n plus 1 raised to the 1 over n. If I take the limit as n approaches infinity, that is infinity to the 0. That's undefined. I introduce e again. E to the natural log of whatever you see. And that would be the limit as n approaches infinity. E, one of the properties of logs, and it becomes identical to the problem we just finished. That would be e to the natural log of 2n plus 1 over n, and that will be e to the limit as n approaches infinity of natural log of 2n plus 1 over n. That is infinity over infinity by L'Hopital. That's the limit as n approaches infinity of e. I forgot the limit. No, I'm sorry. I wrote it wrong. Let me fix it. That would be e to the limit as n approaches infinity. That's 1 over 2n plus 1 times 2 over 1. That would be e to the limit as n approaches infinity. And isn't that 2 over 2n plus 1? As n approaches infinity, that would be e to the 0, which is 1. Therefore, converge. Again, if this was a series, this would have diverged. The following problem, number 18, is a bit tricky. It's kind of challenging to do. I'm going to show you a trick that, I don't know, I think you're going to like. Even though this is a sequence, I'm going to say consider this series n equal 1 to infinity of negative 4 to the n over n factorial. And since this is a series now, can't I use the ratio test? But it's a sequence. That's okay, bear with me. Isn't that negative 4 to the n plus 1 over n plus 1 factorial divided by negative 4 to the n over n factorial? And as we did in class over and over, this is going to be negative 4 to the n times negative 4 to the 1. This is going to be n plus 1 times n factorial times n factorial divided by negative 4 to the n. That's a 4. This cancel with that. This cancel with that. And I notice that this is the limit as n approaches infinity. I'm going to fix that really quick, make it look nicer. And I'm going to fix that right there and make it look nicer. So, wouldn't this be absolute value of negative 4 over n plus 1? And isn't that 0 less than 1? Therefore, the series is absolutely convergent by ratio test. And what do we know? We know from the theorem of test for divergence before we got there, if the series as n approaches 1 to infinity of negative 4 to the n over n factorial converge, then we know that the limit of the sequence equals 0. And everything we need out of this problem is this limit. If we know the limit equals 0, we say therefore the sequence converge. How do you like that trick? You could do that anytime you're running into a factorial, so you have to use those long comparison problems and so on and so forth. Now I want to look at a couple of problems from the next batch of. Okay guys, the next problem says find the sum of the series. Remember, we find the sum of two types of series in this book. One of them is using the geometric series. This is not geometric. And the other one is using telescoping, if you remember. So we're going to try and figure out where this came from. And if you remember, we figured out a nice way of doing this. If I clear the fractions, and if I let n equal 0 and n equal negative 1, basically what the domain restricts, if I let n equal 0, that's the 0. I'm left with a times 1, so I got a to be negative 2. Very good. And if I let n equal negative 1, I'll get negative 2 to equal, this will be 0, plus b times negative 1, so b is 2. So here I figure out that, you know what, this is actually the sum n equal 2 to infinity of negative 2 over n plus 2 over n plus 1. And if I use telescoping, that is, if I look at s sub n, not to infinity, I'll look at the very first term, negative 2 over 1 plus 2 over 2, 2 over 2 plus 2 over 3, plus, and just like we said in class, you don't have to list that many if you are comfortable with this. If not, list few, not a problem, until you really see it. The list goes on, and I notice that this negative 2 over 2 and this 2 over 2 cancel out. And once one whole term cancel out, you do know that everything in between is going to cancel out. And if you're not sure, hey, do you see that this cancel with that? They're going to all cancel out. And if only one term remained, that means I need the very last term. The very last term is literally what we see. I am going to list a few terms just to make sure that you see it. The term before this will be negative over 2n minus 1 and 2 over n. And the term before that would be negative 2 over n minus 1 and 2 over n minus 2. That's a 2 and that's a 1. I'm sorry, backwards. Trying to rush before the 15-minute limit. And if I get those thoughts in place, guess what? I notice that those two cancel out. And I notice that those two cancel out. Again, if only the first term remains, only the last term is going to remain, and a portion of it. So this s sub n is negative 2 plus 2 over n plus 1. And the theorem says you take the limit as n approaches infinity of this s sub n. That's the limit as n approaches infinity of negative 2 plus 2 over n plus 1. And guess what? That will equal a negative 2. Therefore, we say this series converge, and the infinite sum, so let me put it backwards. We say, therefore, the sum n equal 2 to infinity, I started at 2, my mistake, from negative 2 to n plus 1 equal negative 2, and therefore converge. And this is the only time where you don't have to name anything, a theorem or a definition. Alright? And here's the homework that's due with this assignment.